Okay, today we are going to take everything that we have been learning so far about the mole and try to organize it into one nice, neat area that I like to call the mole map. And this document will be extremely important to you for the rest of the semester. You know, when we come back from spring break, we'll be learning all about stoichiometry, which is based on the mole. So you will want to create one of these and take great care of it. Probably keep it with your periodic table, like in that same sleeve. So this document is actually posted. It's linked in the agenda if you would like to if you'd like to have like this hard copy to fill out. Or you can just take a second, pause the video, and sort of draw it out. And I used to do that personally too, just with the boxes and the arrows. Just be really careful as we're going along that you make sure your arrows are pointing in the same direction. They are significant. Remember, this is a map, so this is showing us how we go about solving mole problems. So with that in mind, let's go ahead and start by filling in the center box. The center box here represents the mole. Okay, and the mole is our, foundation in chemistry. Everything is always about getting back to the mole. And the reason that the mole is so important is because this is how we count atoms. So I'm just going to add that to the top so that we remember this. How we count atoms. And remember that we can't actually physically count out these individual atoms or even count a mole. The value of it is so ridiculously huge that we have to have another way to count them, and that's by measuring. And we can measure in mass or we can measure in liters. And so we've looked at 4 different ways to measure over the last couple of weeks. So we've talked about grams, right? We've also talked about liters of a gas at STP. That was one situation, right? And then we talked about liters of gas not at STP. Okay, so liters. Grams, of course, I'm going to go back and add this as mass in case you forget, right? Liters is volume. So this is volume. This is volume. I'm going to just add that right there. And then finally, this is the last thing that we just finished up talking about. We have liters of solution. And again, this is a volume. So we learned about all the different ways that you can go from a unit that you can measure in the lab to the mole, so you know exactly how many atoms or molecules are present. Or if you've done some calculations and you know the number of atoms or molecules present, if you know the number of moles, how you can go back out to these units so you can go and do the measuring in the lab. So let's start with grams. Remember that the way that we can convert from grams to moles or from moles to grams is by using molar mass. And of course, remember that we get molar mass off the periodic table. So I'm just going to add that. That's from the periodic table. And you know, I'm lazy like an electron, so I'm just going to write PT. Okay, we use molar mass. And the conversion fact that we use is that 1 mole of any substance is equal to that number of grams. And again, that's our molar mass that comes from the periodic table. So that's our conversion fact. And we take that conversion fact and we write it different ways based on what we're trying to do. So if our given is in grams, then we take our conversion fact and we write it as a fraction so that the number of grams is on the bottom and 1 mole of the substance is on the top. So if we're going from grams, notice my arrow, I'm going from grams to moles, then I'm going to multiply by 1 mole over grams because that will cancel my grams, right? Because my given is in grams. And again, that number is from the periodic table. Okay, now again, if I'm going back from the mole to the gram, we use the same conversion fact, but we write it a different way. So if I'm starting with moles and going to grams, then what I'm going to do is multiply by the molar mass over 1 mole. And setting it up that way allows us to cancel our units. And again, that's from the periodic table. I'm saying again a lot tonight. All right. So that was the first thing that we learned about, and you guys did great with that. Then we started talking about how gases are really, really tiny and actually don't have very big mass. And in fact, to get like a large measurable mass, you have to have this huge volume of them. And so they're difficult to just put on scales. So instead, when we are dealing with gases, we're going to measure them based on the space that they take up. And this was originally where the mole was developed from. So we have two different settings to deal with gases. We have them when they're at STP and when they're not at STP. This is kind of lab situation. Everybody in the world recognizes what STP means and knows, what you have to set your dials to in your lab. Whereas this is what you use when, you're trying to do calculations about the gas that's in your classroom or something like that, or that's inside of a balloon. Okay. So let's start with the liters of gas at STP. So we can use here that one conversion fact that states that 1 mole of any gas, 1 mole of any gas is equal to or takes up 22.4 liters of space. So no matter whether that's hydrogen gas or oxygen gas or nitrogen or carbon monoxide or carbon dioxide or hydrogen disulfide, whatever you can come up with that's a gas, if it's held at these specific conditions, then this is the conversion fact that you can use. And again, whenever we have conversion facts, we can set up our calculations in this format. We just do unit analysis. So if my given is liters of gas at STP, then I'm going to take this conversion fact and write it as a fraction. I'm going to multiply the given by that conversion fact. And if my given is liters, then I would want the 22.4 liters to be on the bottom and the 1 mole on the top. And when I take my given in liters and multiply it by this fraction, I'm going to be left with moles. Now, if I'm starting with moles and trying to get to liters at STP, again, I'm going to use that same conversion fact, but I'm going to write it as a different fraction. In this case, since I'm starting with moles, the 1 mole will go on the bottom and the 22.4 liters will go on the top. So I'm making this so easy for you guys. It's probably too easy, right? Okay, so that's when we have them at STP, nice and easy. But what happens if the conditions change? And remember that gases are very susceptible to changes in pressure and temperature. They have drastic changes. So we needed a way to calculate them when there is that change off of STP. And that's when you use the ideal gas law that says that the pressure times the volume is equal to the number of moles times a constant times T. Okay, and a couple of things that we need to remember about this equation. First of all is the value of R. Remember that is a constant and it varies based on the units that you're using. Because we're always going to be using atmospheres, we're going to use a value of R of 0.08206. Okay, and then I'm going to try using a different color here. I don't know if this will show up. T, of course, is in temperature and it has to be in kelvins. And remember, we do that by adding to the degrees Celsius, we add 273. N is our moles. Volume is going to be in liters. And then pressure is in atmospheres. And again, you must use those particular units in order for this constant of 0.08206 to be true. If you change any of those variables, then that would change the value and you would need to look it up. Okay. So again, just like we did up here, what we're going to do now is talk about how do we take this equation and manipulate it. If I'm given liters of a gas not at STP, how do I go up here to the mole? So if I'm trying to solve for mole, that's N. I need to get N all by itself. So I just rewrite that equation where I've moved all the variables away from it. And so we're going to do N is equal to PV over RT. So I just take my pressure times my volume, divide by R, divide by T. And I'm just going to put a note on here that we multiply the top and divide the bottom Remember, that's where people get that problem wrong, is that they try to multiply one of the numbers on the bottom and then it gets all kind of messed up. And that's actually true for any of those equations. Okay, so that's how we go from liters to moles. Now, what happens if we're going from moles and we're going out to try to find the volume of a gas that's not at STP? Same equation, but we're going to solve for volume this time. And so we're just going to take that and get V all by itself, which means we're going to fling the pressure over to the other side. So volume is going to be equal to N times R times T divided by P. And again, make sure you're paying close attention to the arrows, the direction that they're going. That's how you choose which, situation or math, equation that you use to solve. All right. Finally, we have liters of solution, right? And remember that a solution is made up of the solute and the solvent. The solvent is water, and we don't care about the water in a chemical reaction. It's not actually involved. What we're concerned about is the solute. And so we have to know how much solute there is per total amount of solution. So we have to know how much there is in the particular volume. And so we do that with concentration. And there's lots of ways to describe concentration, but we're going to focus on molarity. And remember, since we're talking about moles, I think that makes sense that we're doing something that sounds like moles. Molarity sounds a lot like moles. So molarity is represented with a capital M, and molarity is equal to the moles of solute divided by the volume of solution. And of course, it's very important that volume is in liters. So just speaking of that idea that it has to be in liters, I'm just going to put a little asterisk over here that to go from milliliters to liters, you're going to divide by 1,000. Okay, put a little star there so you can kind of remember that. So just in case you're given a volume in milliliters, which you probably will be, you can easily convert it out to liters. All right, so let's say that we know the volume of a solution and we want to try to figure out the moles. If we know the volume of the solution, they're also going to have to give us the molarity. They're going to have to tell us the concentration. So if we're trying to find moles, we're going to rewrite this equation where moles is alone. So to go from volume to the mole, we have to know the concentration. And we simply take the molarity, the concentration, and multiply it by the volume. And again, the volume has to be in liters. So maybe I'll add that. Must be in liters. Okay, and then the reverse, if we know the number of moles that we need, like let's say we've done the math and we know the concentration of the solution, we're just trying to figure out like what volume do I need to get, like pour out of the bottle of the solution in order to have that number of moles. We're just going to take this equation and now we're going to solve it for volume. That's a little bit trickier because volume is on the bottom. So what we're going to do is move volume up to the top, but then volume's not alone, it's with molarity. So then we can move molarity back over to the other side. And so volume, which of course is in liters, is equal to the number of moles of solute that you have divided by the molarity. Okay? And that is your mole map, friends. And if you didn't get that filled out as I was going through it, definitely take a moment, pause this video, and get that all written out. And be very careful about what you put where, because it's really important that you have the arrows pointing in the right directions. Slow responding today, sorry.